For my redo of standard 1.3, I chose to do problem 1.16, and the problem asks us to consider the spin components of a beam of atoms that are prepared in the state, some arbitrary quantum state, and are measured, and the following experimental probabilities are obtained. And it wants us to determine the input state, which is right here. So the probability of obtaining the eigenvalue an in a measurement of the observable A on the system that is prepared in the state is this, where the bra an, or the ket an, is the normalized eigenvector of A corresponding to the eigenvalue an. So let's consider an arbitrary quantum state where we have our eigenvectors and our two constants out in front representing the relative phase. So let's use our experimental probabilities in the definition of the probability of an eigenvalue an to solve for these constants. So since we're talking about a beam of atoms that are we can assume that they're spin 1/2, so we're just going to have a spin up or a spin down eigenvalues, so that those will be our ANs. So knowing that, let's start with probabilities along the z-axis. So for spin up and spin down, they're both probabilities equal to 1/2. So we go through, we use our matrix representations, and we find that 1/2 is equal to the modulus of A squared and the modulus of B squared. But we can choose the phase angle of one of the constants to be 0. So, and then the other one to be an angle theta. So let's choose the phase angle for A to be equal to 0. So then A is just equal to 1 over root 2, and the phase angle for B will be theta. And so B is equal to 1 over root 2 times e to the I theta. So now let's solve for probabilities along, or let's solve for theta, and let's use our probability along the x-axis to do this. So for spin up in the x direction, the probability of a quantum measurement is 3 over 4. So we plug that in, and we plug in our values for A and B in. So A equals 1/2, and B equals, A equals 1 over root 2, and B equals 1 over root 2 times e to the I theta. And we go through, and we plug those in, and we take the modulus squared. So we get the complex conjugate times the original. So that's where this minus I theta term comes from. Go through, and we find that theta is equal to pi over 3. And then for the y-axis in the spin up direction, we do the same thing. Plug in 1 over root 2 for A and 1 over root 2 times e to the I theta for B. Take the modulus squared, and we solve for theta, and we find that theta is equal to negative pi over 3 for theta for a spin up on the y, a measurement on the spin up in the y direction. And doing the same thing in the negative directions, we find the same theta values. For spin down on the x-axis, theta equals pi over 3. Spin down y-axis, theta equals negative pi over 3. But so it can't be theta can't be equal to pi over 3 and negative pi over 3. So we can look here, and we see if we plug in a negative pi over 3, then this will still be equal to 1. But if we go down here and we plug in a positive pi over 3, we'll get a different answer. So that tells us that our coefficient B has to be equal to 1 over root 2 e to the negative I pi over 3, because it satisfies for all the probability measurements. So therefore, our input state is this. And this is my redo of standard 1.3.